Welcome to This Explainer. Today we're diving into something absolutely crucial in computer science, the stack data structure. We're going to take this core programming concept and translate it into relatable everyday logic, so you can actually spot the invisible architecture running your digital life.
Have you ever stopped for a second while browsing and just wondered, how exactly does the browser remember which page to go back to when you hit that back button? Or how software like Photoshop just magically lets you undo that one bad brushstroke? We totally take these features for granted, right? But under the hood, your computer relies on a super specific, elegant little system to keep track of it all. So, here's the roadmap for today's explainer. First, stack and LIFO. Second, the main operations of a stack. Third, how a stack works. Fourth, real uses of stack. And finally, number 5, code of a stack in C++. Let's jump right in.
Section 1. Stack and LIFO. All right, so at its core, a stack organizes data using one golden rule, the LIFO principle. LIFO. That stands for last in, first out. It literally means whatever piece of data enters the stack last absolutely has to be the very first one to come out. There's no reaching into the middle, and you definitely can't pull from the bottom. It is a strictly top-down operation.
To really picture this, just think of a physical stack of coins on your desk, or maybe a tall stack of plates at a buffet. When you're stacking those coins, you always drop the new one right on top, right? And when you need a plate at the canteen, you don't yank one out from the bottom. You'd knock the whole thing over. You take the topmost item first. The very last plate the kitchen staff put on the pile is the first one you pick up. That's LIFO in action.
Moving on to Section 2, main operations of a stack.
Okay, so there are two heavy hitters when it comes to stack operations. First up is push. Pushing simply means adding a new element, and, as we just established with LIFO, this new data gets added strictly to the top. The direct opposite of that is pop. Popping means removing an element, and yep, you guessed it, this removal happens exactly at the top too. You push onto the top and you pop off the top. It's an incredibly controlled, predictable flow of information.
Now, because we're always dealing with limited computer memory, we've got to use some supporting checks before we make any moves. We use a check called isEmpty to see if the stack actually has anything in it. If your program tries to pop an item from a completely empty stack, the computer basically panics and throws an overflow error. On the flip side, if we're working with a stack that has a strict size limit, isFull is our best friend. It prevents an overflow error, which happens if you try to push data onto a stack that's already maxed out. These checks are absolutely crucial safety nets.
And there's one more super handy operation called peek, though you'll sometimes hear it called top. Imagine you're playing cards and you just sort of lift the corner of the top card to peek at it without actually drawing it from the deck. That is exactly what peek does. It lets the computer view that topmost element and read its value without actually pulling it off the stack.
Section 3. How a stack works.
Let's put this all together and see it in action. Starting with a totally empty stack, for step 1, we execute push 10. Boom, 10 is now our top element. Step 2, we push 20, dropping it right on top of the 10, so our new top is 20. Step 3, we push 30. Now, reading from bottom to top, we've got 10, 20, 30, with 30 sitting pretty at the very top. Finally, in step 4, we issue a basic pop command. Since pop only ever targets the top, that 30 is instantly removed, leaving 20 as our brand new top element. Pretty straightforward, right?
Up next, Section 4, real uses of stack.
So why does all this matter? Well, it turns out stacks are the secret engine behind a massive chunk of modern computing. When you use the undo feature in a text editor or Photoshop, every single action you take is being pushed onto a stack. Hit Ctrl-Z, and the program simply pops your last action right off, reverting to the state underneath it. The exact same logic applies to your web browser history. Every new page is pushed on top, and every click of the back button pops the current page off. Beyond that, stacks manage function calls in computer memory. That's literally how a computer pauses one task to run another and knows exactly where to pick back up. It's also vital for recursion and heavily used by compilers to figure out complex mathematical expressions. Honestly, stacks are just silently organizing our digital chaos every single second, proving that sometimes the simplest rules really do create the most powerful systems.
And finally, Section 5, code of stack in C++.
Translating all this theory into actual code is incredibly straightforward. Taking a look at a basic C++ application, we can create a stack specifically designed to hold integers. Following our exact scenario from earlier, the code just sequentially calls push 10, push 20, and push 30 to build it up. Next, if we ask the program to print the top function, it outputs 30. Then, after calling the pop function, that 30 is gone, and printing the top element one last time confirms our new top is indeed 20. It's honestly just super satisfying to see that LIFO logic play out perfectly in just a few lines of code.
Whether you're mashing the back button on your web browser or a computer is managing complex memory allocations behind the scenes, this LIFO principle is just a universally powerful tool. So now that you've mastered the mechanics, it leaves a really fascinating question. Take a look at the software you use the most every single day. Where else is a hidden stack silently keeping your digital world from completely collapsing? Think about it, and let that curiosity drive your next coding adventure.